Good evening. My name is Lukas Kiesewetter, and I'm a junior studying mechanical engineering. This year, I worked with Dr. Shaw on our research project, modeling flight and battery dynamics for electric aircraft. So to begin with a quick background, we've seen significant progress in EVs over the last decade. You're starting to see electric cars and trucks in the news a lot more and on the roads. However, what many people don't know is aviation is also heading in this direction. Organizations across the world have set the very ambitious goal to have net zero carbon emissions by the year 2050 from the aviation sector. This necessitates the design of new aircraft that can handle electric propulsion systems and new battery systems that can handle the steep demands that flight requires, because it's much harder to fly an airplane than it is to drive a car. The issue with this, as all of these new designs are currently in development, is their information is either proprietary or simply just non-existent. So therefore, we created a paired flight and battery dynamics model that will simulate electric aircraft performance to give the data and information needed to better design these aircraft by the time that they're actually supposed to be used by people. The reference aircraft we're using in our presentation is the EFAN 2.0. So before we get into the modeling side of things, I quickly wanted to talk about what actually goes on inside of a battery. So you have two sides that are each called the electrodes. You have the cathode on the left, which is usually some sort of metal oxide, and the anode on the right, which is usually from graphite. When you charge the battery, a voltage is applied which will break the bond between the metal oxide and the lithium, causing the lithium and electron to go to the other side at the anode. So when it's over here, you can kind of think of this as potential energy or stored energy. Now, when this happens, the metal oxide is electronegative. That means it wants its electrons back. So as soon as you open a pathway for the electrons to return to the other side, they will go through the external circuit and the lithium will go on with it. This is where you actually extract the power of the battery and use it to power something such as an aircraft. So there's several different ways to model this. There's the simple approaches, starting at level 0. We call this level 0 because it doesn't really have any mathematical basis behind it. It's more, and this is the current state of most electric aircraft research today. They essentially look at what sized batteries can produce what power, but don't actually look at what's going on inside of the battery. The next level up is level 1. This is the equivalent circuit model. In the equivalent circuit model, essentially the battery we showed on the last slide is represented by a circuit of resistors and capacitors. So this can show charging and discharging behavior, but again, it doesn't actually show any of the lithium ions. The next models are the physics-based ones. We have the single particle model, where the two electrodes, the anode and cathode, both consist of uniform spherical particles. So it makes the math really simple and easy without sacrificing too much accuracy to what actually would happen in theory. The pseudo two-dimensional model takes this to the next level, looking at the particles in both the horizontal and vertical direction. So it's a bit more accurate, but much more computationally intensive. For our model today, we're using the single particle model. So now that we know kind of the battery side of things, we can move on to flight. We consider a simple fixed-wing plane moving at a velocity v at some flight path angle gamma from the ground. Now, if we say that this velocity and flight path angle will not change, that means that their derivatives are 0. So this is kind of like putting the plane into cruise control. It won't vary the speed often. So the two equations for these derivatives can relate to the four main forces of flight acting on the airplane. You have the weight, which pulls it down, and of course is due to gravity. Next, you have lift and drag. Drag works against the airplane's motion. It's kind of like a wind, very resistive. And then next, you have lift. This is what keeps the airplane flying. It works against gravity. Both lift and drag are functions of the airflow around the airplane's wings, and it also depends on the structure of the aircraft, how it is designed. Finally, we have thrust. Thrust is what is actually produced from your propulsion system. Thrust acts at some angle of attack from the direction of your velocity. Now, if we assume this angle of attack to be very small, we can use the small angle trigonometric approximation. This will simplify the two dynamics equations, which allows us to first solve the bottom one for lift, and then you can plug that in to get drag, since those two are related, and then finally get thrust. The reason we want thrust is this is how we can find the power required that the battery must produce in order for the aircraft to fly. Thrust is multiplied by velocity and divided by some efficiency, eta, and then you can get the battery power. So this successfully links the battery and flight models together, and we can do this all in MATLAB. That is the engineering program we use to simulate all of this. The final part of the model is the rangefinder algorithm, and this has been the focus of the research over the past couple months. So what we do is there's a bunch of complicated differential equations that are in this ODE solver. There's a tool in MATLAB called ODE 15. So if we supply that ODE solver with a list of initial conditions, both on the battery side of things and the flight side of things, as well as an initial range guess, it will come up with some sort of solution. Now the solution we must check to make sure it's a valid case. Essentially, we want to see if the battery discharged too much or if the ODE solver had any problems. If it does not pass the check system, we will decrease the range and try again until we ultimately get a successful solution that will then indicate that we found the range of the aircraft, which is, again, how far it travels, to the nearest 100 meters. So looking at some sample results, in these two case studies, we varied cruise altitude and cruise velocity and looked at their impact on range and endurance. Endurance is how long the aircraft is in the air, and then of course altitude is how high it goes, velocity is how fast it's going. As you can see in these two graphs, there's a clear peak where the best range is obtained at a specific velocity and a specific altitude. So why this might be happening? Looking at the battery side of things, on the first plot on the left, you can see the voltage profile going down over time. This just shows how the battery is discharging. But the key point here is there are three distinct phases: climb, cruise, and descent. So climb is when the aircraft's going up, cruise is when it's at its top altitude, and then descent is when it's landing. So looking at the right graph, you will see discharge C rate and power. These just tell you kind of how hard is the battery working. And so essentially to optimize range, we want to minimize how hard the battery is working. So looking at those cases that we talked about in the last slide with velocity and altitude, if you're working at a really high velocity, that requires more power. Similarly, going to a high altitude means you spend more time at that period where the battery is working hard. On the other side of things, at low altitudes, you have more drag because the air is more dense, so there's more working against you. And then at low velocities, you're moving slower. So again, there's more time spent in that climb phase. So the two extrema, the high end and the low end, are not ideal. And that's where we see in this middle area, there's this ideal altitude and cruise velocity where we get the best range. So in summary, our fixed or combined flight and battery model will look at all of these different parameters that affect both sides and investigate how they have effects on each other. So moving on to some future directions, one of the first things we want to do is add dynamic temperature. Currently we have it that the temperature of the battery will stay constant and not change with time. Secondly, we want to investigate payload capabilities. So essentially, if we add more batteries to the plane, it'll give you more power, but it comes at extra weight. So what's the trade-off there? Thirdly, we want to look at degradation. So how does the battery get worse over time? And then the second main thing we want to do is replace the single particle model with a pseudo two-dimensional model to essentially see how detailed of a battery model do we need to get the same level of accuracy. On the flight side of things, earlier this year, Dr. Shah, I, and some collaborators published a review article in Progress in Aerospace Sciences on electrical vertical takeoff and landing vehicles. So these will take off like a helicopter and then fly like a plane. What we found is that there's a severe lack of battery analysis for these vehicles and not much comparison between them, leading to a lack of convergence in design. So we think if we apply the single particle model to the different flight models of these eVTOLs, we might be able to determine what the best one would be for a specific application. And that is the ultimate goal of this project over the next couple of years. Before concluding, I'd like to quickly thank Dr. Wayne and Dr. Kaluri for their help on the flight and battery model side of things respectfully, and then Owen from my research lab for helping provide some of the battery parameters. With that, we'll now conclude the presentation and open it up to any questions. Thank you.
I assume that your model and inferred that it's just a single battery.
Yeah, so we model a single battery, and then batteries can be scaled up to the pack level through a number of series connections and a number of parallel connections. So essentially, we simulate everything at a single battery, and then we can scale it up to an entire battery pack. So these batteries are like 4 volts. The entire battery pack system is about 250 volts.
So you can build in redundancy and have multiple batteries.
Yes, exactly.
So you mentioned that you were using the single particle model instead of the 2D model. What kind of benefit or value do you think you would get from moving to the more complex battery model?
Yeah, so I guess probably starting with the simpler models, we talked about the equivalent circuit model. The big benefit of that is it's very quick. It's what's used in EVs in their battery management system. So that's the benefit, but when we're wanting to project like the performance of the aircraft, we want to be as accurate as possible. because then this will lead to better planning on logistics side of things and aircraft design. So the pseudo two-dimensional model can handle the electrolyte solution between. The single particle model does not look at the electrolyte at all. And then so there's certain physical behaviors that happen with the pseudo two-dimensional model that couldn't happen in the single particle model. So just getting more accuracy to ensure the safety of these flights would be really big.
So how accurate were your results to the EFAN reference aircraft?
Yeah, so as I mentioned earlier, there's very limited information about electrical aircraft. So even the EFAN, which is by Airbus, they did not publish much information about it. We know it completed a 74-kilometer flight at 160 kilometers per hour. However, there was one article by Kapstov and Rodriguez from the University of Concordia, and they simulated the EFAN. What was interesting is if I go back to the velocity and altitude graphs, so they found higher endurance and range, but it happened at the same cruise altitude and same cruise velocity that we did. The reason we think their endurance and range was higher was because they discharged the battery all the way, and it was linear. But the fact that we obtained the maximum range at the same values indicates that our model is mapping up well against the existing data.
For the future work, what differences will exist in flight models for the different aircraft configurations?
Yeah, so the different eVTOLs, here 3 of them are shown. The multicopter is kind of like a drone. The lift plus cruise and tilt rotor have more like plane characteristics. But the big thing with these is they have vertical takeoff and landing. So I guess going back to our, looking at the forces on the plane, when you're taking off vertically, you lose all of the lift and drag because lift and drag are via the airflow over your plane. So essentially thrust then has to completely counteract the weight to take off. So this will drain the batteries heavily. So that's something that we really have to take into account. And then the only thing that would change beyond that is then once we get to after it's vertically taken off, the rest of the flight model can stay the same, but instead of having the starting point be at the ground, it's at whatever it took off to. But so implementing the different like thrust and the different directions that the velocity is pointing, kind of seen here, like the lift plus cruise, you have one vector pushing this way and a bunch pushing up. So just kind of balancing all of those. So it'll be a big undertaking, and that's why it's kind of the ultimate goal.